Over the last 15 years, global demand for energy has risen by over 50%. This growing demand is largely fueled by increasing population as well as the growing dependence on electrical devices. To meet this demand, more fossil fuels than ever before are being burnt, and consequently pollution levels are rising. Statistics show that over 2 million deaths a year can be attributed to atmospheric pollution, with this figure expected to rise as energy demand continues to soar. This has led to scientists and engineers to push for new, sustainable energy sources with the view of reducing the impact of climate change. Whilst there are many forms of renewable energy, such as geothermal and nuclear generators, wind energy as a solution is becoming increasingly popular due to the relative ease of installation and lack of toxic byproducts. In the past 10 years, the global generation capacity of wind energy has quadrupled, and they now provide over 2% of the world's power. As part of this drive for clean energy, we designed and tested a wind turbine that has been inspired by the same world we are trying to save. For the design of this turbine, we were provided with a number of constraints. Firstly, the turbine should rotate clockwise when viewed from upstream, not exceeding 3000 rpm at a wind speed of 12 meters a second. The tip speed ratio, or TSR for short, referring to the ratio of tangential speed of the blade tip and actual wind speed, must be between 3 and 8. The blade should also be manufactured as one single part and be able to fit in a box of length, depth and height of 400, 100 and 150 mm respectively. The hub of the turbine was to be manufactured out of aluminium. The turbine is to be tested at 4 different speeds and should generate power at all 4 speeds. Any bio-inspired or original features would also be viewed desirably.
Following these constraints, we identified 3 key goals we wanted to achieve with our design. First, we aimed to hit the maximum RPM of 3000 at 12 meters per second. This will allow our blade to generate the most power. Next, we decided on a TSR of 4.5. Using the data from QBlade, we found that the optimal TSR is approximately 5.5. However, to avoid exceeding the maximum RPM of 3000, we chose a more conservative value of 4.5. Lastly, we decided to prioritize the structural integrity of our blade, since mass was not a concern, meaning we could have thicker blades with no penalty. The larger the diameter of the turbine, the more power generated. To ensure that our blade satisfies the given dimensions and yet have additional diameter, we decided on printing it in the internal diagonal. This increases the diameter of the turbine to 410 mm. Using existing research papers on airfoils for small horizontal axis turbines, 4 types of airfoils were shortlisted. To get an idea of how the airfoils will perform in practice, we used QBlade to simulate its performance. Airfoil profile was obtained from the UIUC airfoil database, which were later used to draw the blade in Creo. To optimize performance whilst preventing structural failure or excessive tip deflection, we decided to use a combination of 2 airfoils. They are the SG6040 and SG6043 airfoils. We decided to use the SG6040 airfoil closer to the root of the blade, where structural stresses are higher since it is much thicker. Closer to the tip, however, we used the SG6043 blade profile as the structural stresses were lower and the angular velocity is higher. Using the approach of 2 airfoil sections introduced the problem of deciding at what stage to blend the SG6040 to the SG6043. Analysis suggested that the blending of the SG6040 to the more aerodynamic SG6043 at about 20% blade radius was the optimal compromise for structural integrity and performance. When designing the turbine, it is important to remember that turbine blades generate more power with larger surface areas and incident airspeeds. Due to the rotation of the turbine, the tip of the blade has a higher tangential velocity than the root of the blade. Hence, less surface area is required at the tip of the blade than at the root. This means that the blade can be tapered to minimize the force required to make it rotate. Further, using QBlade, we obtained an optimal angle of attack of 4.5 degrees. Due to the different rotational speeds, however, the effective angle of attacks at different positions of the blade are different with the same wind direction. Blade twist is hence needed to keep the angle of attack consistent. Using MATLAB, chord lengths and twist angles along the blade were calculated using the Schmidt's formula, with the blade discretized into 20 parts. The nose cone plays an important part in the aerodynamic performance of the turbine. To reduce drag generated by the nose cone, we used the formula governing the Hack series shapes of nose cone, developed by Wolfgang Hack to determine the optimal shape. The resulting shape helped us determine the diameter of the hub. The length of the hub was then determined based on the chord length of the blade root.
A key characteristic of our blade is its sweep, which was inspired from the wings of the common swift. Spending more of their lives in flight, swifts have evolved to become one of the best flyers around. The common swift has long, swept-back wings that resemble a boomerang, that aid in fast gliding motions. Leading-edge vortices, or LEVs, have been shown to be beneficial in leaf generation. Studies on the bird's wings have concluded that its sweep geometry is able to generate and maintain a stable LEVs across the range of angle of attacks. Hence, we modeled after the wings of the swift. However, the sweep was minimal, so as not to compromise the turbine structural integrity. We also placed vortex generators on our blades, similar to the tiny peaks on a dragonfly's wings that generate swirling vortices. The vortices led to a turbulent boundary layer, which is less likely to separate, hence the legend stall. The height of the vortex generators is that of the boundary layer and are placed to an angle to incoming flow near the leading edge of the blade, so that flow at the trailing edge is turbulent. With all design parameters done, we finally made a model of our turbine on Creo.
After we had finalised our design, the next step was to manufacture our turbine. Our blade was manufactured using a rapid prototyping procedure, thus allowing us to directly 3D print our blade from the Creo parametric CAD files. Whilst that process went on, we could manufacture our hub. From a solid block of aluminium, we used a lathe to create the hole in the centre of our hub and to create a cylindrical shape. After this had been done, we used a CNC machine to create the final hexagonal shape we desired from the cylinder. A hydraulic press was used to cut the keyway after the shape had been formed, and a drill was used to drill the hole into the side. Then the hub was complete. When the turbine had been printed, it was very rough on the surface, partly due to printing it on the diagonal. We used increasingly finer sandpaper to smooth the surface transitions and to round the edges in the hub to get a very smooth finish. In this process, we had to sand off vortex generators due to their minute size. Following this, we laser cut the vortex generators out of plastic and used adhesive to secure them onto the blades after sanding. Finally, we placed the hub into the printed turbine and we were ready for testing.
As the test results are concerned, two sets of data were obtained, one with the vortex generators VG added to the blades and one without it. In the first experiment with the VGs, the power obtained was expected for a turbine of 410 mm of diameter. From the graph shown, we obtained the following results. Note that no data was obtained for 6 meters per second, as the turbine stopped when the brakes were applied at this velocity for both sets of experiments. Finally, note that the results obtained were slightly lower for the non-VG case, showing their importance and effectiveness.
Having tested the turbine and analysed its performance, it is obvious several design improvements could be made. Firstly, it was clear the structural considerations were overly conservative. Whilst this led to a strong turbine that displayed little blade deflection, decreasing the thickness of the blade, as well as choosing a more aerodynamically efficient aerofoil at the root as opposed to the SG6040, could lead to a better design with better aerodynamic characteristics, while still being structurally operational. The implementation of the vortex generators along the length of the blade could also be changed. Whilst the vortex generators improved the turbine performance in their current configuration, future design iterations may wish to consider placing the vortex generators along the entire length of the blade, rather than just the inboard half. This may allow the angle of attack of the blade to be more aggressive, thus generating more lift. Reducing the mass of the turbine may also lead to greater performance. Low mass and thus low rotational inertia requires less force to turn, and so lowering the mass of the design may have allowed us to generate power at a wind speed of 6 meters a second. Lowering the mass could be achieved by decreasing the sectional thickness of the blade. Additionally, the hub could be lightened by shortening its length as well as removing material by drilling holes through the sidewalls.